Hello. In today's video, we're going to be looking at Chapter 16, Lecture 13, Learning Objectives 2 and 3. We're going to look at conjugate acid-base pairs. We're going to look at acid and base strength. And we're going to look at the autoionization of water, bringing in our first equilibrium, new equilibrium constant for this chapter. Okay, so a conjugate acid-base pair is going to be a set of, or two chemical species that differ by only by the presence of one proton. So, a pair of chemical species that differ by the presence of one proton. Okay, so when a substance loses a proton or gains a proton, that would be a conjugate acid-base pair. So a conjugate acid is going to be a species formed after a base accepts a proton. Specifically one proton. And then a conjugate base is going to be the species formed after a acid donates one proton. Okay? And the thing about a conjugate acid-base pair, you have your acid, and then after it's lost that proton, it becomes a base, which is called the conjugate base. And then if you have a base, once it accepts a proton, it goes from being a base to a acid, and we call it the conjugate acid. So let's take an acid such as acetic acid. Okay. And we're going to react it with water. Okay, and I'm going to take this hydrogen right here. We're going to follow its progress. It's going to go from here, and it's going to donate over here. And what we're going to produce is a species with one fewer proton, so it'll get a negative charge, and a species with one additional proton. Which we call hydronium. Okay? So, in the forward direction, this is our acid, and it donates protons, so this is our base. However, in the reverse reaction, this will donate to here, so this is now an acid. And this is a base. So this would be our conjugate acid and our conjugate base. So if we look at our conjugate acid-base species, CH3CO2H and then CH3CO2 minus would be our conjugate acid-base species, and then H2O, H3O plus conjugate base acid pair. So the species which is more positive will be the one that is the acid. So in this case, our CH3CO2 minus has a negative charge, so it would be the more negative, so it would be the base, and then the CH3CO2H, our acetic acid, has a neutral charge, so it would be more positive in our acid. Okay? They can only, a conjugate acid base pair can only differ by one proton though. So if we look at something like sulfuric acid and hydrogen sulfate, these differ by one proton, so they are a conjugate acid base pair. And then if we lose one more proton, we get another conjugate acid base pair, but H2SO4, SO4 2- are not conjugate acid base pairs, while these two are. Okay, so let's try some examples out. Let's look at the following species. So we've got a couple different substances, and we want to know what the conjugate acids of the following are. So the conjugate acid is a species that is formed after a base accepts a proton. Okay, so in the following example, we want to determine which one will be our, or what species will be conjugate acid base pairs. So we need to add a proton in each of these. So here, we're going to have a proton boop, 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 being added here. So we get CH3, C, O, O, H, H, and we get a positive charge there. Same idea here. To get that conjugate acid-base pair, if we're starting out with a base, we need to add in a proton. So we get that right there. Here we get HCN. Here we get HSO4 minus. Hopefully you guys notice that anytime we add in a proton, we either become more positive or less negative. Like so. Okay. We can do the opposite. We can, instead of getting a conjugate acid, we can form our conjugate bases. So what happens as we remove a hydrogen from each of these? So here we have ClO4 minus, HS minus, PH3, CO3 2 minus, and then lastly hydroxide. Okay. So continuing on, let's look at the acid-base properties of water. So water itself can act as an acid or a base. It depends on what it's put in, right? So if water is put in with an acid, it's going to act as a base. If water is put in with a base, it's going to act as an acid. So we call this this idea that water can donate or accept a proton, amphiprotic. because water can both act as an acid or a base, if it is pure by itself, there is going to be some amount of reaction between two water molecules, one acting as an acid, one acting as a base. And when this occurs, we have what's called autoionization of water. Where two water molecules collide, they transfer a proton from one to the other, producing a conjugate acid and a conjugate base. So here we have two water molecules. One of the water molecules loses a hydrogen. One of them gains a hydrogen. So this hydrogen goes over there. And we produce hydronium and hydroxide. This will happen in any aqueous solution. Or in pure water. So in both cases, there's going to be some concentration of hydronium and hydroxide. Okay, so because this is an equilibrium process, we can tell that because of this, we have an equilibrium constant that goes with it, called the ion product constant of water, or Kw. So that is going to describe basically the concentrations of hydronium and hydroxide within pure water or within a aqueous solution. So this Kw can be written as the hydronium concentration times by the hydroxide concentration. Remember, with any equilibrium constant, it's going to be products over reactants. Our reactants are water, which is in the liquid phase, so they are not included in the Kw expression. If we have pure water at 25 degrees Celsius, then we have a Kw equal to 1.0 times 10 to the negative 14. So from this, we get our concentrations of each species equal to 1.0 times 10 to the negative 7. If we have an acidic solution, our hydronium concentration will be greater than our hydroxide concentration. So that hydronium concentration will go up, that hydroxide concentration will go down. If we have a basic solution, then we will have our hydroxide concentration going up, hydronium concentration going down, and then in pure water, where we have a pH of 7, we will have equal concentration of hydronium and hydroxide as long as we are at 25 degrees Celsius. If we are not at 25 degrees Celsius, that number will change slightly. Okay, so we want to determine what the hydroxide concentration is when our hydronium concentration is 1.35 times 10 to the negative 4, and then what our hydronium concentration is if our hydroxide concentration is 5.75 times 10 to the negative 8. So we can always say, okay, Kw is equal to OH minus times by hydronium. So our Kw, 1.0 times 10 to the negative 14 is equal to hydroxide concentration times by our hydronium concentration, which is in this case 1.35 times 10 to the negative 4. So we're going to divide that 1.0 times 10 to the negative 14 by 1.35 times 10 to the negative 4. we get a value of 7.41 times 10 to the negative 11, which, since we have a hydronium concentration greater than that 1 times 10 to the negative 7, we would say that it is acidic. It's an acidic solution. And as such, we would have a lower hydroxide concentration. Okay, now we're looking at the hydronium concentration. Here, we're at 5.75 times 10 to the negative 8. If we notice here, we are a hydronium concentration lower than that 1.0 times 10 to the negative 7. So we are, again, in an acidic solution. So we will have a hydronium concentration that is greater than a hydroxide concentration. So we're going to again put this in. 1.0 times 10 to the negative 14 is equal to our hydroxide concentration times by our hydronium concentration. So 1.0 times 10 to the negative 14 times by our hydroxide concentration. And then our hydronium concentration. Multiply this out, or rather divide 1.0 times 10 to the negative 14 by 5.75 times 10 to the negative 8. We get a hydronium concentration of 1.82 times 10 to the negative 7, so greater than that 1.0 times 10 to the negative 7, which again indicates to us that we have a acidic solution. Okay, that is everything for lecture learning objectives 2 and 3. We will continue with 4 and 5.